Hello, James again with the last problem of the semester. This is homework 10, problem 5, and it concerns this circuit. So the circuit starts out with the switch closed, and it's been closed for a long time. So the inductor is basically wire because the inductor voltage has a magnitude that is L times the magnitude of the time derivative of the current. Well, after a long time, the circuit has reached its steady state. So there's no longer any change in the current. So the inductor acts like a wire. Uh, for a capacitor in series, after a long time, the capacitor acts like an open switch because it's fully charged and it has the battery voltage. But now it's in parallel, not in series. So basically the capacitor acts like a wire too. And so this is just battery and resistor. This is for time before you open the switch. So I'll call this time less than 0. But close to the time you open the switch. In other words, it's the circuit's been sitting for a long time. So I'll say before you open the switch, time less than 0, but absolute value of time small. So in other words, shortly before you open the switch. So this is just a battery and a resistor and nothing else. Two ideal wires are the same as one ideal wire. The current in the circuit you find from Ohm's law is just that. And there's a bit of an odd wording here. It says no voltage. The switch is closed for a long time. No voltage is measured across the capacitor. That is, it's fully charged. Well, no voltage across the capacitor means that there's no charge on the capacitor, since the capacitance is charge over voltage, or its voltage is charge over capacitance. So the fact that there's no voltage measured across the capacitor means there's no charge on the capacitor, but it's the same thing as saying it's fully charged, because in this circuit, as time goes to infinity, the full charge is 0. Okay, so it's just an odd way to say it. Anyway, what happens in the circuit, if you forget my poor notation here, what happens in the circuit if you leave the switch closed for a long time is basically the circuit becomes equivalent to a battery and a resistor. So this is the current before you open the switch. After you open the switch, you have just the inductor and the capacitor. So for time equal to 0, greater than or equal to 0, the circuit is just the inductor and the capacitor. So it's an LC circuit. And what the inductor does at time 0, remember the inductor opposes changes in the current. Well, when you open the switch, what the inductor does is it tries to maintain the current that existed immediately before the switch was opened, which was this. So in other words, the inductor creates or maintains the current when you open the switch, so that at time 0, when the switch is just opened, the current is equal to EMF over R. And if you remember, for the LC circuit, the current has the functional form I at time 0 times cosine of omega t, where omega is 1 over root LC, which you can find from solving the differential equation that you get by looking at the loop rule for this circuit. So that is your current as a function of time. The inductor voltage magnitude is L times the magnitude of di dt. So it's L I at time 0. Derivative of cosine with respect to time is minus sine, but we're taking an absolute value, so we don't really care about the sign. And the chain rule says that you bring out an omega. So what we're interested in this problem, in this problem, is the maximum potential difference across the capacitor. The maximum potential difference across the capacitor is the same as the maximum potential difference across the inductor because of the loop rule. When VC is a max, VL has to be a max going the other way so that the sum of the two is 0. So in other words, VC max is equal to VL max by the loop rule, which is this, L I at time 0 times omega, which is 1 over root LC. And so it's equal to, I'll just simplify a little bit, L over root L. I get I at time 0 times root L over C. And I at time 0, as I talked about before, is just EMF over R. So EMF over R, root L over C. And we're given this maximum voltage for the capacitor, 150 volts, and we want to find L. So we say that VC max is equal to EMF over R root L over C, and we want to solve for L. Well, we square both, multiply by R over EMF on both sides, and you get that root L over C is equal to VC max times R over EMF. I just multiplied by R over EMF on both sides. I want to get L by itself, so I square both sides. I get L over C is equal to VC max R over EMF squared. And L is what I want, so multiply by C on both sides. So I get L is equal to C VC max R over EMF squared. And if I plug in the numbers I was given, C is 0.5 microfarads. So I guess let me go down here. C is 0.5 times 10 to the negative 6 farads times VC max is 150 volts times R is 250 ohms divided by EMF, battery EMF, which is 55 volts. And that's squared, and I'll pause to calculate. And that comes out to be 0.232 henries. So there were a few moving parts here. The main ideas are what the circuit is doing after a long time with the switch closed, and then what it's doing immediately after the switch is open. So the things to remember here are that as time goes to 0 minus, for calculus notation. In other words, as time goes to right before you open the switch, the circuit goes to battery and resistors so that the current is just given by Ohm's law. After you open the switch, so that the circuit becomes just the, remember I'm talking about this switch, so that the circuit with the switch open is just these two things, the inductor and the capacitor. So the other thing to remember is that when you open the switch so that time goes to 0 plus, in other words, right after time 0, the circuit is just the inductor and the capacitor, and the inductor keeps the current what it was immediately before the switch was opened. So basically, the things to remember about this problem are that as time goes to 0 plus, right after you open this, the switch, the current is EMF over R. Because as time went to 0 minus, that was the current, and the inductor strives to maintain the current. And then from there, it's just analysis of an LC circuit, remembering the functional form of the current and the angular frequency. Okay, so I'll move the problem into frame before I close it out, and hope this was of use, and thank you for your time, and thank you for watching over the course of the semester, and have a great day. Good luck on the exam.